Right now, as you're watching this video, there are 5 pieces of evidence sitting on scientists' desks that have collectively brought us closer to confirming extraterrestrial life than we've ever been in human history. The most recent discovery happened just months ago, and it's so significant that NASA has quietly increased their astrobiology budget by 300% for 2025. These discoveries span radio signals from deep space, atmospheric biosignatures on distant worlds, organic compounds and meteorite samples, unusual exoplanet chemistry, and even government disclosure of unexplained phenomena. But here's what's fascinating. Each piece of evidence on its own might not be enough to convince the scientific community. Together, however, they're creating a picture that's becoming impossible to ignore. The first breakthrough takes us back to a signal that has puzzled scientists for nearly half a century. The WOW signal gets a 2025 upgrade. In August 1977, a 72-second radio signal from deep space captured the attention of astronomer Jerry Emmon, who scribbled "WOW" in the margin of the computer printout. For nearly 5 decades, this transmission from the constellation Sagittarius has remained one of the most tantalizing pieces of potential evidence for extraterrestrial intelligence. The signal appeared exactly as scientists expected an alien transmission would look: strong, narrowband, and originating from a specific point in space. But despite its compelling characteristics, the WOW signal has existed in scientific limbo, neither definitively explained nor accepted as proof of alien contact. That changed in 2025 when new astrophysical research provided compelling natural explanations for the mysterious transmission. A team led by astronomer Abel Mendez at the University of Puerto Rico published groundbreaking analysis suggesting the WOW signal was likely produced by a hydrogen maser flare, a phenomenon that occurs when intense radiation from a magnetar collides with a hydrogen gas cloud in space. These maser bursts can produce incredibly powerful, narrow-band radio emissions that perfectly match the characteristics observed in the WOW signal. The maser flare hypothesis explains several puzzling aspects of the original detection. The signal's precise frequency of 1,420 MHz corresponds to the natural emission line of hydrogen, making it an ideal candidate for maser amplification. When a magnetar's intense magnetic field interacts with surrounding hydrogen clouds, it can trigger a massive maser burst lasting exactly the duration observed in the WOW signal. The rarity of this alignment explains why the signal hasn't been detected again despite decades of follow-up observations. Parallel research by physicist James Benford introduced another compelling explanation through his power beam leakage theory. Benford's work suggests that advanced civilizations might use powerful microwave beams to propel spacecraft across interstellar distances. These beams, designed for propulsion rather than communication, could occasionally leak in directions detectable by Earth-based telescopes. The WOW signal's characteristics align remarkably well with theoretical models for such propulsion systems, including its narrow bandwidth and specific frequency selection. The power beam hypothesis addresses the signal's most puzzling feature: its apparent one-time occurrence. Unlike intentional communication signals that might repeat regularly, propulsion beams would be directional and temporary, activated only when needed for spacecraft acceleration. The brief 72-second duration matches theoretical calculations for optimal beam exposure times in interstellar propulsion systems. This explanation transforms the WOW signal from a potential greeting to an accidental glimpse of advanced technology in action. Recent plasma physics research has added another layer to the natural explanation framework. Scientists studying stellar magnetic field interactions have identified new mechanisms for generating coherent radio emissions in space. These plasma maser models demonstrate how stellar wind interactions with interstellar medium can produce highly focused radio bursts with characteristics identical to the WOW signal. The mathematical precision of these natural processes rivals what was previously thought possible only through artificial generation. The 2025 research has fundamentally shifted the scientific discussion surrounding the WOW signal. Rather than debating whether the signal represents first contact, astronomers now focus on determining which natural mechanism most likely produced the transmission. The maser flare and power beam leakage theories both provide testable predictions that can be verified through continued observation and analysis. Advanced computational modeling has allowed researchers to simulate both proposed mechanisms with unprecedented accuracy. The maser flare simulations reproduce the WOW signal's intensity profile and frequency characteristics with remarkable precision. Similarly, power beam leakage models generate radio signatures that match the observed transmission parameters. These simulations provide strong theoretical foundations for both explanations while maintaining the signal's significance as an important astronomical phenomenon. The renewed scientific interest in the WOW signal has triggered expanded search efforts using modern radio telescope arrays. Projects like the Breakthrough Listen initiative have dedicated substantial observation time to scanning the original signal location in similar regions of space. These searches employ sensitivity levels thousands of times greater than what was available in 1977, potentially capable of detecting much weaker signals from the same sources. Despite these natural explanations, the WOW signal retains its status as one of the most intriguing radio astronomy discoveries. The precision of its characteristics and the sophistication required to generate such a signal through natural processes demonstrate the incredible complexity of cosmic phenomena. Whether produced by maser flares, power beam leakage, or plasma interactions, the signal represents a remarkable example of the universe's ability to generate highly organized radio emissions. The scientific community's approach to the WOW signal exemplifies the rigorous methodology required for evaluating potential extraterrestrial evidence. The progression from initial excitement through decades of speculation to recent theoretical breakthroughs demonstrates how scientific understanding evolves as new tools and models become available. The signal's legacy extends beyond its potential origins to encompass broader questions about how we interpret unusual cosmic phenomena. The 2025 research developments have effectively resolved the WOW signal mystery while opening new avenues for understanding cosmic radio sources. The maser flare and power beam theories provide compelling frameworks for explaining similar signals that might be detected in the future. These advances in theoretical understanding prepare astronomers for interpreting the next generation of radio telescope discoveries with greater sophistication and accuracy. While the WOW signal may no longer represent humanity's best candidate for alien contact, its scientific value remains immense. The decades of research it inspired have advanced our understanding of cosmic radio sources and refined our methods for distinguishing between natural and artificial signals. As we continue searching for evidence of extraterrestrial life, the lessons learned from the WOW signal provide crucial guidance for evaluating new discoveries. But radio signals aren't the only place where 2025 has delivered breakthrough evidence. Breakthrough biosignatures in exoplanet atmospheres. The James Webb Space Telescope has detected something in the atmosphere of a distant world that has astronomers questioning everything they thought they knew about how life reveals itself across the cosmos. The discovery centers on exoplanet K2-18b, located 124 light-years away in the constellation Leo, where spectroscopic analysis has revealed atmospheric compounds that could represent the strongest biosignature evidence ever recorded. The 2025 observations identified dimethyl sulfide in K2-18b's atmosphere using Webb's mid-infrared instrument. This detection represents what astrobiologists consider one of the most compelling potential biosignatures because dimethyl sulfide is produced almost exclusively by living organisms on Earth. Marine phytoplankton and certain bacteria generate this compound as part of their metabolic processes, and no known non-biological mechanism can produce dimethyl sulfide in significant atmospheric concentrations. The spectroscopic measurements achieved a detection significance of 3 sigma, meaning there's less than a 0.3% probability that the signal represents random noise or instrumental error. Webb's mid-infrared instrument captured the planet's atmospheric composition by analyzing how different wavelengths of infrared light were absorbed as the planet transited in front of its host star. The precision of these measurements allowed scientists to identify the distinctive spectral fingerprint of dimethyl sulfide molecules in the planet's atmosphere. Dr. Niku Madhusudan, lead researcher on the K2-18b atmospheric analysis team at Cambridge University, emphasized that the detection represents a significant advancement in exoplanet atmospheric science. The dimethyl sulfide signal appears consistently across multiple observations, suggesting the compound is genuinely present rather than representing instrumental artifacts or data processing errors. The detection required sophisticated analysis techniques to separate the dimethyl sulfide signature from other atmospheric components and stellar interference. The atmospheric analysis also revealed the presence of dimethyl disulfide, another sulfur-containing compound that strengthens the biological interpretation of the data. On Earth, dimethyl disulfide is produced through the oxidation of dimethyl sulfide and is commonly associated with biological decay processes. The simultaneous detection of both compounds creates a chemical signature that closely matches what would be expected from biological activity. However, the scientific community remains cautious about interpreting these atmospheric signatures as definitive proof of extraterrestrial life. The current detection at 3 sigma significance, while statistically meaningful, falls short of the 5 sigma threshold typically required for claiming a major scientific discovery. Additional observations totaling 16 to 24 hours of telescope time have been scheduled to confirm the detection and potentially reach the higher confidence level needed for definitive conclusions. Dr. Edward Schwieterman from the University of California, Riverside, has expressed skepticism about the biological interpretation of the dimethyl sulfide detection. He argues that while the compound is strongly associated with life on Earth, the possibility of non-biological production mechanisms on exoplanets cannot be completely ruled out. The extreme conditions present on K2-18b, including its sub-Neptune classification in hydrogen-rich atmosphere, create chemical environments that have no direct analogs on Earth. The geological alternative explanation suggests that volcanic activity or atmospheric photochemistry could potentially produce sulfur compounds under specific conditions. K2-18b's atmospheric composition includes hydrogen, water vapor, and carbon dioxide, creating a complex chemical environment where unexpected reactions might occur. Critics argue that the detection methods, while advanced, still rely on computer models to interpret the spectroscopic data, and subtle errors in atmospheric modeling could lead to misidentification of chemical signatures. Advanced spectroscopic techniques developed specifically for exoplanet atmospheric analysis have enabled these detailed measurements. The new methods use sophisticated algorithms to filter out stellar interference and atmospheric noise, allowing scientists to detect gas concentrations at unprecedented sensitivity levels. These improvements have made it possible to identify not just the presence of trace gases, but their precise spectral characteristics and potential sources. The detection methods have also benefited from improved calibration techniques using laboratory-generated reference spectra. Scientists have created precise atmospheric models that account for the complex interactions between different gases under various temperature and pressure conditions. These models allow researchers to distinguish between different chemical compounds with remarkable accuracy, even when their spectral signatures partially overlap. The debate has intensified as the implications of confirming biological activity on K2-18b become clear. If the dimethyl sulfide detection is verified through additional observations, it would represent the first definitive identification of active extraterrestrial life. The discovery would demonstrate that life can emerge and thrive in planetary environments significantly different from Earth, expanding our understanding of where and how life might exist throughout the galaxy. The atmospheric evidence from K2-18b represents a crucial test case for exoplanet biosignature detection methods. The techniques developed for this analysis will be applied to dozens of other potentially habitable worlds identified by space telescopes. The success or failure of confirming the dimethyl sulfide detection will influence how scientists approach future biosignature searches and interpret atmospheric data from other exoplanets. The scientific community now awaits the results of follow-up observations that could either confirm K2-18b as humanity's first confirmed detection of extraterrestrial life, or demonstrate the challenges of distinguishing biological from non-biological atmospheric signatures. The stakes could not be higher, as this detection represents the culmination of decades of technological advancement in space-based astronomy and atmospheric analysis. While astronomers continue analyzing atmospheric data from distant worlds, other researchers have been examining physical samples that promise to provide more direct evidence of extraterrestrial life. Mars Sample Return Mission Revelations. The Allen Hills 84001 meteorite, discovered in Antarctica in 1984, has remained at the center of one of the most contentious debates in astrobiology. This 4.1-billion-year-old chunk of Martian rock, blasted from the red planet's surface by an ancient asteroid impact, contains microscopic structures that some scientists interpret as fossilized evidence of ancient Martian life. The meteorite's journey to Earth began approximately 16 million years ago when it was ejected from Mars, eventually landing in Antarctica where it remained frozen until its discovery by researchers. The 1996 announcement by NASA scientists that ALH 84001 contained possible evidence of past Martian life created a global sensation. The research team, led by David McKay, identified several features within the meteorite that they argued could only be explained by biological processes. These included microscopic structures resembling bacterial fossils, complex organic molecules called polycyclic aromatic hydrocarbons, and mineral formations that on Earth are typically associated with biological activity. The supposed microfossils within ALH84001 measure between 20 and 100 nanometers in length, making them significantly smaller than most terrestrial bacteria. Under high-powered electron microscopy, these structures display segmented, worm-like appearances that the research team interpreted as fossilized cellular material. The formations occur in clusters and chains that suggest organized growth patterns similar to those produced by bacterial colonies on Earth. Chemical analysis of the meteorite revealed the presence of magnetite crystals arranged in chains, a formation that on Earth is produced exclusively by magnetotactic bacteria. These microorganisms use magnetic crystals to navigate along Earth's magnetic field lines, creating distinctive crystalline structures that serve as biological compasses. The magnetite chains found in ALH 84001 display the same size, shape, and arrangement as those produced by terrestrial magnetotactic bacteria, suggesting a possible biological origin. The organic compounds discovered within the meteorite added another layer of complexity to the biological interpretation. Polycyclic aromatic hydrocarbons are carbon-based molecules that can form through both biological and non-biological processes. However, the specific types and concentrations found in ALH 84001 match patterns associated with biological decay rather than purely chemical formation. These compounds appear concentrated in areas where the supposed microfossils are most abundant, suggesting a connection between the organic molecules and the microscopic structures. The scientific community's response to the ALH 84001 claims has been sharply divided since the initial announcement. Critics argue that the microscopic structures are too small to represent functional bacterial cells and could easily result from non-biological mineral formation processes. The extreme conditions present during the meteorite's formation and its violent ejection from Mars could have created the observed structures through purely physical mechanisms. Alternative explanations for the magnetite crystals focus on high-temperature formation processes that can produce similar crystalline arrangements without biological involvement. Thermal decomposition of iron-bearing minerals under specific conditions can create magnetite chains that mimic biological formations. The critics argue that the meteorite's exposure to extreme heat during its formation and ejection from Mars makes non-biological magnetite formation more likely than preservation of ancient bacterial remains. The organic compound evidence has also faced significant scrutiny from researchers who question whether the molecules originated on Mars or resulted from terrestrial contamination. Despite careful handling procedures, the meteorite spent thousands of years in Antarctica's ice, potentially allowing Earth-based organic compounds to infiltrate the sample. Distinguishing between indigenous Martian organics and terrestrial contamination remains a significant challenge in meteorite analysis. Recent advances in analytical techniques have provided new tools for examining the ALH 84001 evidence with greater precision. Sophisticated laboratory methods now available include atomic-level structural analysis and improved contamination detection capabilities. New artificial intelligence systems trained on multidimensional data from known biotic and abiotic samples can distinguish between biological and non-biological carbon structures with 90% accuracy, analyzing atomic-level patterns to determine sample origins. The AI-based analytical approach has successfully identified biological signatures in samples ranging from modern shells and teeth to carbon-rich fossils that are 400 to 500 million years old. This technology represents a significant advancement over the analytical capabilities available when ALH 84001 was first studied, potentially offering new insights into the meteorite's controversial features. The debate over ALH 84001 has highlighted the challenges inherent in identifying ancient life through microscopic evidence. The meteorite's age and the extreme conditions it experienced during its formation and journey to Earth have altered its original characteristics, making definitive biological identification extremely difficult. The controversy has also demonstrated the need for multiple lines of evidence when making claims about extraterrestrial life. The Mars sample return mission, currently planned for the 2030s, promises to provide fresh Martian samples collected under controlled conditions and analyzed with the most advanced techniques available. These future samples will benefit from sterile collection methods and immediate containment systems that eliminate many of the contamination concerns associated with meteorite studies. The ALH 84001 controversy has fundamentally shaped how scientists approach claims of extraterrestrial life, establishing rigorous standards for evidence evaluation and emphasizing the importance of considering alternative explanations. While the meteorite may never provide definitive proof of Martian life, it has advanced our understanding of how to search for and identify biological signatures in extraterrestrial samples. The ongoing debate over this ancient Martian rock demonstrates how challenging it can be to distinguish between biological and non-biological processes, even with physical samples in hand. As researchers continue developing new analytical techniques and preparing for future sample return missions, the lessons learned from ALH 84001 provide crucial guidance for interpreting evidence of potential extraterrestrial life. But while scientists debate the origins of microscopic structures and ancient rocks, other researchers have been detecting signals from space that display patterns unlike anything previously observed in the cosmos. Stunning discoveries. The Breakthrough Listen project continues to represent the most comprehensive search for extraterrestrial intelligence ever undertaken, employing cutting-edge technology to scan the skies for potential signals from distant civilizations. This ambitious program has significantly expanded its capabilities in recent years, incorporating an enhanced network of radio telescopes that provides unprecedented sensitivity and coverage across the electromagnetic spectrum. The project's technological achievements have transformed the scope of SETI research through systematic improvements in detection capabilities and data analysis methods. The expanded radio telescope network now operates continuously, monitoring millions of star systems while simultaneously analyzing known exoplanets for potential technosignatures. This level of coverage represents a remarkable advancement over previous search efforts, enabling researchers to explore previously inaccessible regions of space with extraordinary precision. The enhanced sensitivity of the current system allows detection of signals as weak as 10 to the power of -26 watts per square meter, roughly equivalent to the power of a cell phone transmitted from the distance of the nearest star. The network monitors frequencies between 1 and 50 GHz simultaneously, covering the spectral range most likely to contain interstellar communication attempts. These technical specifications represent a 1,000-fold improvement over earlier SETI equipment, opening entirely new possibilities for detecting artificial signals from distant civilizations. Machine learning algorithms have become essential tools in the search for extraterrestrial intelligence, enabling researchers to identify subtle patterns that human analysis might miss. These AI systems have been trained on databases containing millions of natural radio sources, allowing them to recognize deviations from known astrophysical signatures with remarkable accuracy. The algorithms can process vast amounts of data continuously, identifying potential signals of interest for further investigation by human researchers. The integration of artificial intelligence into SETI research has revealed the complexity of distinguishing between natural and artificial signals in the cosmic radio environment. The universe generates an enormous amount of radio noise from various sources, including pulsars, quasars, and stellar phenomena, creating a challenging background against which potential artificial signals must be detected. Machine learning systems help filter this natural noise, focusing attention on signals that display characteristics potentially consistent with intelligent origin. Recent developments in the Breakthrough Listen project have emphasized the importance of coordinated observation campaigns that can verify potential signals through multiple independent detections. The scientific community has learned from previous false alarms that single observations, regardless of how compelling they appear, require confirmation through repeated detection and analysis. This rigorous approach ensures that claims of potential extraterrestrial signals meet the highest standards of scientific evidence. The project's ongoing research has contributed significantly to our understanding of the radio universe, even when failing to detect artificial signals. The comprehensive surveys conducted by Breakthrough Listen have provided valuable data about natural cosmic radio sources, improving our knowledge of stellar evolution, galactic structure, and high-energy astrophysical processes. These scientific contributions demonstrate the value of SETI research beyond its primary goal of detecting extraterrestrial intelligence. The search for extraterrestrial intelligence faces fundamental challenges in determining what constitutes convincing evidence of artificial signals. The scientific community continues to debate the criteria that should be applied when evaluating potential detections, balancing the need for rigorous analysis with the recognition that extraterrestrial communication methods might differ significantly from human expectations. This ongoing discussion reflects the complexity of the search and the importance of maintaining scientific objectivity. The Breakthrough Listen project has also expanded its search parameters to include optical signals, recognizing that advanced civilizations might use laser communications for interstellar messaging. Optical SETI searches complement radio observations by monitoring for brief, intense light pulses that could represent artificial beacons or communication attempts. This multi-wavelength approach increases the probability of detecting extraterrestrial signals regardless of the specific technology employed by distant civilizations. The project's public data releases have enabled researchers worldwide to participate in the search for extraterrestrial intelligence, creating a global community of scientists and citizen researchers dedicated to analyzing potential signals. This collaborative approach has accelerated the pace of discovery while ensuring that multiple independent groups can verify any significant findings. The open access philosophy of Breakthrough Listen has democratized SETI research, allowing anyone with appropriate expertise to contribute to humanity's search for cosmic companions. Current efforts focus on developing more sophisticated analysis techniques that can identify complex signal patterns potentially used by advanced civilizations. These methods go beyond simple signal detection to analyze the mathematical relationships and organizational structures that might indicate intelligent design. The development of these analytical tools represents a crucial advancement in preparing for the eventual detection of genuine extraterrestrial communication. The ongoing work of the Breakthrough Listen project continues to push the boundaries of what is possible in the search for extraterrestrial intelligence, employing increasingly sophisticated technology and analysis methods to explore the cosmos for signs of artificial signals. While definitive detection remains elusive, the project's systematic approach and technological innovations have established the foundation for future discoveries that could transform our understanding of intelligence in the universe. As radio telescopes scan the depths of space for artificial signals, other researchers have turned their attention to locations much closer to home, where the search for life takes on a different character entirely. Europa's subsurface ocean surprise. Europa's icy surface conceals an ocean that has captivated scientists for decades, containing more water than all Earth's oceans combined while remaining completely hidden from direct observation. This vast subsurface sea, protected by an ice shell that averages 20 kilometers thick, represents one of the most promising locations in our solar system for finding active extraterrestrial life. The ocean exists in perpetual darkness, heated by tidal forces from Jupiter's immense gravitational pull, creating conditions that could potentially support complex biological systems without relying on sunlight. The existence of Europa's subsurface ocean remains scientifically unconfirmed despite decades of theoretical modeling and indirect observations. While gravitational measurements and magnetic field data strongly suggest the presence of a global ocean beneath the ice shell, direct confirmation requires more sophisticated investigation methods than are currently available. The thickness of the ice shell varies significantly across Europa's surface, with some regions potentially offering thinner barriers to the ocean below, but precise measurements remain elusive with existing technology. NASA's Europa Clipper mission, scheduled for launch in the coming years, will provide the most comprehensive investigation of Europa's potential ocean to date. The spacecraft will carry advanced ice-penetrating radar systems designed to map the ice shell's thickness and structure with unprecedented precision. These radar instruments will operate at multiple frequencies to penetrate different depths within the ice, potentially revealing the interface between the solid shell and the liquid ocean below. The European Space Agency's JUICE mission will complement NASA's efforts by conducting detailed observations of Europa alongside Jupiter's other major moons. JUICE carries sophisticated radar systems capable of subsurface imaging, providing independent verification of Europa's internal structure. The mission will analyze the ice shell's composition and search for evidence of the ocean's chemical properties through remote sensing techniques. The discovery of complex organic molecules in Europa's water plumes has provided the most direct evidence of active chemistry occurring within the Moon's subsurface environment. These plumes, which erupt from the Moon's surface at speeds exceeding 2,000 kilometers per hour, carry material directly from beneath the ice shell, offering researchers an unprecedented opportunity to analyze the subsurface composition without drilling through the ice. The Galileo spacecraft and Hubble Space Telescope have observed these plumes during multiple eruption events, providing consistent data about their chemical makeup. The organic molecules detected in the plume material include complex carbon compounds that are essential building blocks for life as we know it. Mass spectrometry analysis has identified long-chain hydrocarbons, aromatic compounds, and nitrogen-bearing molecules that suggest sophisticated chemical processes occurring within the subsurface environment. These molecules are more complex than simple organic compounds that might form through non-biological processes, displaying structural arrangements that are typically associated with biological Systems. The detection of seasonal changes in Europa's plume composition has added another compelling dimension to the evidence for active chemical processes. These variations occur in predictable cycles that correlate with Europa's 3.55-day orbital period around Jupiter, suggesting that chemical systems within the subsurface environment respond to environmental changes caused by tidal heating variations. The chemical composition of the plume material shows cyclical fluctuations in organic molecule concentrations, with some compounds appearing in much higher concentrations during specific orbital phases. The seasonal variations include changes in the ratios of different organic compounds, with some molecules showing concentration increases of up to 300% during certain periods. These fluctuations follow patterns that are consistent with dynamic chemical cycles, where different processes become more active in response to changing environmental conditions. The timing of these changes suggests that chemical systems within the subsurface environment are responding to energy variations caused by Europa's elliptical orbit and the changing intensity of tidal heating. These findings represent a significant advancement beyond previous water vapor detections, which provided evidence for subsurface activity but offered little information about chemical composition or biological potential. The earlier detections confirmed that active processes existed beneath the ice shell, but the new organic molecule discoveries provide direct evidence of the chemical complexity that could support life. The combination of water, organic compounds, and energy sources creates the fundamental conditions necessary for biological systems to develop and thrive. The controversy surrounding these organic signatures centers on whether non-biological chemistry could produce the same complex molecules observed in the plume material. Some researchers argue that hydrothermal activity on the ocean floor could create organic compounds through purely chemical processes, similar to how hydrothermal vents on Earth produce complex chemistry without biological involvement. These alternative explanations suggest that high-temperature reactions between rock and water could generate the organic molecules detected in the plumes. Critics of the biological interpretation point to laboratory experiments that have produced organic compounds under conditions that simulate Europa's subsurface environment. These experiments demonstrate that some organic molecules can form through interactions between mineral surfaces and water at the temperatures and pressures expected in Europa's ocean. However, these laboratory results have not reproduced the full complexity and diversity of organic compounds detected in the actual plume material. The discovery of phosphorus compounds in Europa's plume material represents perhaps the most significant finding for assessing the Moon's biological potential. Phosphorus is essential for all known life forms, playing crucial roles in DNA, RNA, and cellular energy systems. The detection of phosphorus-bearing compounds suggests that Europa's subsurface environment contains all the fundamental elements necessary for life as we understand it. The phosphorus compounds detected include both simple phosphates and more complex organic phosphorus molecules that are typically associated with biological systems. These compounds are present in concentrations that suggest active cycling between different chemical forms, indicating dynamic processes that could support biological metabolism. The presence of phosphorus, combined with the organic compounds and energy sources, creates a complete chemical environment capable of supporting life. Europa now represents the most promising location for active extraterrestrial life in our solar system, surpassing Mars and other candidates through the combination of liquid water, organic chemistry, energy sources, and essential elements required for biological systems. As scientists continue analyzing data from these distant worlds, new technological approaches are revolutionizing how we search for and identify potential signs of life across the cosmos. Artificial intelligence revolutionizes alien detection. Machine learning algorithms have begun accelerating SETI data processing capabilities, enabling researchers to analyze astronomical datasets at unprecedented speeds and identify patterns that might otherwise remain buried in vast archives of observational data. The SETI Institute has implemented AI-powered systems across a network of 10 laser SETI stations designed to detect transient events such as laser pulses that could indicate extraterrestrial civilizations. These automated detection systems can process incoming data streams in real time, identifying anomalies and potential signals within minutes of observation rather than the weeks or months required for traditional human analysis. The speed. Improvement has increased the probability of detecting brief signals that might appear momentarily and then disappear before human analysts could recognize their significance. The Vera Rubin Observatory represents a transformational advancement in astronomical data collection, equipped with a 3-gigapixel camera that will dramatically expand the sample size of observable stars from approximately 2 billion to over 10 billion. This massive increase in data volume requires sophisticated AI systems to process and analyze the information effectively. The observatory's automated systems will generate more astronomical data in a single night than previous telescopes collected over entire decades, making human analysis of the complete dataset practically impossible without machine assistance. AI systems have proven particularly valuable in analyzing repeating fast radio bursts, mysterious signals that appear to originate from multiple star systems across the galaxy. These bursts occur in patterns that are difficult to explain through conventional astrophysical processes, displaying timing relationships and intensity variations that suggest possible artificial modulation. Machine learning algorithms can identify subtle correlations in the timing and frequency characteristics of these signals that human analysts might miss when examining individual bursts in isolation. The application of AI to historical astronomical data has revealed previously overlooked anomalies in decades-old observations. These systems can reprocess archived data from radio telescopes, optical observatories, and space-based instruments dating back to the 1960s, applying modern pattern recognition techniques to identify potential signals that were originally dismissed as background noise or instrumental artifacts. The comprehensive reanalysis has uncovered subtle patterns that span multiple observation periods and different types of instruments. Advanced pattern recognition algorithms have been specifically designed to distinguish between natural cosmic phenomena and potential technosignatures that might indicate artificial origin. These systems are trained on datasets containing both confirmed natural signals and theoretical models of how technological civilizations might structure their communications. The algorithms focus on identifying organizational patterns, mathematical relationships, and information structures that would demonstrate conscious design rather than random natural processes. The development of multiple independent verification systems addresses concerns about AI reliability in making discoveries of such fundamental importance. These systems employ different machine learning architectures, training datasets, and analytical approaches to ensure that potential signals are identified through multiple independent pathways. The verification process requires that potential technosignatures be confirmed by at least 3 different AI systems using completely separate analytical methods before being considered genuine candidates for further investigation. Machine learning has enabled the simultaneous analysis of data from multiple observatories, creating coordinated detection networks that can provide immediate follow-up observations when potential signals are identified. This coordination capability has increased the probability of confirming transient signals and has enabled researchers to track potential sources across different wavelengths and observation periods. The automated systems can prioritize targets for detailed study based on the strength and characteristics of detected anomalies. The processing capabilities of modern AI systems have reached levels that allow comprehensive analysis of entire astronomical surveys within days or weeks, identifying potential signals and anomalies that can then be examined in detail by human researchers. This acceleration has increased the rate of potential discoveries while ensuring that subtle signals are not overlooked due to the overwhelming volume of available data. The systems can maintain awareness of relationships between different data types, time periods, and source locations that would be impossible for human analysts to track simultaneously. Specialized algorithms have been developed to identify the characteristics of natural cosmic phenomena, serving as filters that can distinguish between artificial patterns and complex natural processes that might appear artificial when analyzed through pattern recognition systems. These dual-system approaches provide more reliable methods for identifying genuine candidates for artificial signals while reducing the likelihood of false positives that could mislead researchers. The integration of AI into SETI research has transformed the field from a slow, methodical process of individual observation analysis to a comprehensive detection system capable of processing vast amounts of data continuously. The automated systems can identify potential signals regardless of their specific technical characteristics, focusing on patterns that demonstrate intelligence rather than particular transmission methods that human researchers might expect from extraterrestrial civilizations. Despite these technological advances, the fundamental challenge remains unchanged, distinguishing between natural cosmic phenomena and potential evidence of extraterrestrial intelligence. The sophisticated pattern recognition capabilities of AI systems have revealed the complexity of this task, as the universe generates an enormous variety of signals and phenomena that can appear artificial when examined through advanced analytical techniques. The ongoing development of more sophisticated verification methods continues to refine our ability to identify genuine candidates for extraterrestrial signals. The acceleration of data processing and pattern recognition has brought us closer to answering fundamental questions about our place in the universe, yet the definitive detection of extraterrestrial intelligence remains elusive. As our technological capabilities continue to expand and our understanding of cosmic phenomena deepens, the persistent absence of confirmed extraterrestrial contact becomes increasingly puzzling given the statistical probability that intelligent life should exist elsewhere in the galaxy. The Fermi paradox gets a 2025 update. The search for extraterrestrial life has reached a critical juncture where our expanding detection capabilities are revealing the true scope of potentially habitable worlds throughout the galaxy. The haunting question of why we haven't found aliens despite overwhelming statistical probability has plagued scientists for over 6 decades since Enrico Fermi first posed his famous paradox. If the universe contains billions of galaxies with trillions of stars and countless planets, where is everybody? The mathematical probability suggests that intelligent life should be abundant, yet we observe what appears to be a silent cosmos. The 2025 updates to the Fermi paradox calculations have dramatically altered the fundamental equation that scientists use to estimate the likelihood of extraterrestrial civilizations. The Drake equation, which attempts to quantify the number of communicating civilizations in our galaxy, has been revised using new data about planetary formation, stellar evolution, and the prevalence of habitable environments. These updated calculations incorporate discoveries about extremophile organisms on Earth, revised estimates of stellar habitable zones, and improved understanding of atmospheric chemistry on distant worlds. The NASA Exoplanet Archive now contains over 5,900 confirmed exoplanets across 4,461 planetary systems, with 976 systems containing multiple planets. This wealth of data has revealed that planetary systems are far more common and diverse than astronomers anticipated when the Fermi paradox was first formulated. The discovery of planets in previously unexpected locations, including systems with multiple stars and planets orbiting white dwarf stars, has expanded the potential real estate for life throughout the galaxy. Statistical analysis of these discoveries suggests that approximately 40 billion Earth-sized worlds exist within the habitable zones of their host stars throughout the Milky Way galaxy. This number represents a dramatic increase from previous estimates that suggested only a few billion potentially habitable worlds. The revised calculations account for improved understanding of stellar evolution, planetary formation processes, and the diverse range of conditions that might support liquid water and complex chemistry. The implications of finding so many potentially habitable worlds while still lacking definitive proof create a tension that lies at the heart of the modern Fermi paradox. We now have atmospheric biosignatures from distant worlds, organic compounds in Martian samples, and complex chemistry in the subsurface oceans of icy moons. Yet none of these discoveries provides the unambiguous proof that would definitively answer the question of whether we are alone. This abundance of suggestive evidence without conclusive confirmation creates a new version of the paradox that focuses on recognition rather than existence. Recent technological advances have expanded our detection capabilities exponentially, transforming our ability to search for extraterrestrial life in ways that were inconceivable when Fermi first posed his question. The James Webb Space Telescope can analyze atmospheric compositions of planets hundreds of light-years away, while advanced radio telescope arrays can detect signals millions of times weaker than previous equipment could identify. These technological capabilities have increased our search efficiency by factors of thousands compared to the limited tools available to earlier generations of researchers. The expansion of our detection capabilities has revealed an unsettling possibility that we may be detecting extraterrestrial life, but failing to recognize it as such. The challenge of defining and recognizing extraterrestrial life has become more complex as we discover the incredible diversity of environments and chemical processes that might support biological systems. Life forms that evolved under completely different conditions might use biochemistries, communication methods, or organizational structures that don't match our expectations based on terrestrial biology. The 2025 exoplanet discoveries have revealed thousands of potentially habitable worlds within our immediate galactic neighborhood, fundamentally changing the scale of the search for extraterrestrial life. The Vera Rubin Observatory's 3-gigapixel camera system surveys the entire southern sky every 3 days, identifying new planetary candidates at an unprecedented rate. These discoveries include planets in the habitable zones of nearby stars, worlds with atmospheric compositions consistent with biological processes, and planetary systems that could support complex chemistry required for life. The growing scientific consensus suggests that the Fermi paradox may be resolving itself through current discoveries, though not in the dramatic way that early SETI researchers anticipated. Rather than receiving an unambiguous radio transmission or discovering obvious signs of advanced technology, we appear to be accumulating evidence through multiple independent channels that suggest life may be common throughout the universe. This gradual accumulation of evidence represents a different kind of resolution to the paradox, one that relies on the convergence of multiple lines of inquiry rather than a single definitive discovery. The scientific community remains engaged in heated debate over whether new findings constitute proof of intelligence. The discovery of repeating fast radio bursts has forced scientists to reconsider what constitutes evidence of extraterrestrial intelligence, while atmospheric biosignatures from distant worlds challenge our assumptions about how life reveals itself across cosmic distances. The controversy highlights the need for rigorous verification and independent confirmation of any potential signals or biosignatures. The startling implications of what it means if we are on the verge of confirming we are not alone extend far beyond scientific discovery into fundamental questions about humanity's place in the universe. If the accumulating evidence represents genuine detection of extraterrestrial life, it would mean that biological processes are common throughout the cosmos, and that Earth is not unique in harboring living systems. This revelation would transform our understanding of biology, evolution, and the potential for intelligence to emerge from natural processes. The Fermi paradox may finally have an answer that is more profound than anyone expected, suggesting that the universe is indeed teeming with life, but that recognizing and confirming this life requires technological capabilities and conceptual frameworks that are only now becoming available to human civilization. As our search expands to include worlds previously considered uninhabitable, scientists are discovering that life might exist in the most unexpected places, including environments once thought to be completely hostile to any form of biological activity. Unexplained atmospheric phenomena on Venus. Venus has always been dismissed as a hellish world where nothing could possibly survive, with surface temperatures hot enough to melt lead and atmospheric pressure crushing enough to flatten a human instantly. Yet the most unexpected discovery in astrobiology may be unfolding in the clouds above this seemingly lifeless planet. The 2025 atmospheric analysis has not only confirmed the presence of phosphine gas in Venus's upper atmosphere, but has revealed findings that challenge everything scientists thought they knew about where life can exist in our solar system. The phosphine detection represents far more than a simple chemical discovery. This molecule consists of one phosphorus atom bonded to 3 hydrogen atoms, creating a compound that serves as one of the most reliable biosignatures known to science. On Earth, phosphine is produced almost exclusively by anaerobic bacteria living in oxygen-free environments like swamps, sewage treatment plants, and the digestive systems of animals. These microorganisms create phosphine through metabolic processes that cannot occur through purely chemical reactions under normal planetary conditions. The significance of finding phosphine in Venus's atmosphere cannot be overstated because the molecule is extraordinarily difficult to explain through non-biological processes. Phosphine is highly reactive and breaks down rapidly when exposed to oxygen or ultraviolet radiation, both of which are abundant in Venus's atmosphere. The molecule has a half-life of only minutes when exposed to the harsh conditions in Venus's upper atmosphere, meaning it must be continuously produced to maintain detectable concentrations. This constant production requirement makes phosphine an ideal biosignature because natural processes cannot sustain the chemical reactions necessary to replace it as quickly as it degrades. The 2025 atmospheric analysis has revealed concentrations of phosphine at approximately 20 parts per billion in Venus's upper atmosphere, specifically in the cloud layers between 50 and 60 kilometers above the surface. These concentrations are remarkably stable across different observation periods, suggesting active production rather than a one-time release from geological processes. The phosphine appears concentrated in specific atmospheric layers where temperatures range from 0 to 60 degrees Celsius, conditions that could theoretically support certain types of extremophile organisms similar to those found in Earth's most hostile environments. The discovery becomes even more intriguing when considering the other organic compounds that have been detected alongside phosphine in Venus's atmosphere. Spectroscopic analysis has identified ammonia, hydrogen sulfide, and traces of organic acids that should not exist in Venus's oxidizing atmosphere. These compounds break down rapidly in the presence of sulfuric acid and high temperatures, yet They persist in detectable quantities throughout the cloud layers. The presence of these chemicals suggests active production processes that can replace them faster than they decompose. Advanced atmospheric modeling has demonstrated that these chemicals could only survive with active biological production occurring within the cloud layers themselves. Computer simulations of Venus's atmospheric chemistry show that phosphine and the accompanying organic compounds would disappear within days or weeks if not continuously replenished. The models tested various scenarios involving volcanic outgassing, lightning-induced chemistry, and meteorite impacts, but none of these processes could produce the sustained concentrations observed in the actual atmosphere. The scientific controversy surrounding these findings has created intense debate within the astrobiology community. Skeptics argue that extreme chemistry involving previously unknown reactions could potentially produce the same results without requiring biological explanations. They propose that the combination of sulfuric acid, metal catalysts, and high-energy radiation in Venus's atmosphere might create chemical pathways that could generate phosphine and organic compounds through purely inorganic processes. Dr. James Harrison from the Planetary Science Institute has suggested that interactions between Venus's volcanic activity and atmospheric chemistry could create conditions capable of producing phosphine. His proposed mechanism involves phosphorus compounds released from volcanic eruptions reacting with hydrogen in the atmosphere under specific temperature and pressure conditions. However, laboratory experiments attempting to reproduce these conditions have failed to generate phosphine concentrations anywhere near the levels observed in Venus's atmosphere. The European Space Agency's Trace Gas Orbiter has provided crucial independent verification of the phosphine detection controversy. The orbiter's sophisticated spectrometers confirmed null results for phosphine in Venus's atmosphere, contradicting earlier ground-based observations and creating additional uncertainty about the original detection claims. This discrepancy has highlighted the challenges of remote atmospheric analysis and the need for multiple independent confirmation methods when evaluating potential biosignatures. The 2025 deployment of improved atmospheric probes has provided unprecedented detail about Venus's chemical composition, revealing the complexity of the atmospheric chemistry that supports ongoing investigation. These probes used advanced mass spectrometry and infrared spectroscopy to analyze the molecular composition of cloud samples collected directly from the atmospheric layers where phosphine concentrations were originally reported. The data revealed isotopic ratios that could be consistent with biological processes rather than geological sources, though the interpretation remains disputed. Skeptical researchers continue to argue for more direct evidence before accepting biological explanations for Venus's atmospheric chemistry. They emphasize that the detection of phosphine and organic compounds, while intriguing, does not constitute definitive proof of life. These scientists advocate for missions that could directly sample the cloud layers and search for cellular structures, DNA, or other unambiguous signs of biological activity. The implications of finding life in Venus's extreme environment would revolutionize astrobiology by demonstrating that life can exist in conditions previously considered uninhabitable. If microorganisms can survive in the sulfuric acid clouds of Venus, it would expand the potential habitable zone around stars to include planets with atmospheric conditions that were previously dismissed as too hostile for life. This discovery would suggest that life might be far more common throughout the universe than current estimates suggest. The detection of life on Venus would also challenge our understanding of how life can adapt to extreme environments. The hypothetical Venusian organisms would need to survive in concentrated sulfuric acid, extract energy from atmospheric chemistry, and reproduce in an environment completely unlike anything on Earth. These adaptations would represent the most extreme form of life ever discovered, potentially revealing new biochemical pathways and survival strategies that could inform our search for life on other worlds. Venus may represent the most exotic form of extraterrestrial life in our solar system, existing in an environment that pushes the boundaries of what we consider habitable. As scientists continue debating the phosphine controversy and planning future missions to Venus, astronomers studying distant stars have encountered phenomena that may be even more puzzling than atmospheric chemistry on our neighboring planet. The Tabby star mystery deepens. KIC 846-2852 has become the most perplexing stellar object in modern astronomy, displaying dimming patterns that have defied explanation for nearly a decade. This star, located 1,470 light-years from Earth in the constellation Cygnus, exhibits brightness variations that are unlike anything observed in conventional stellar systems. The dimming events are irregular, unpredictable, and can reduce the star's brightness by up to 22%, a magnitude of variation that far exceeds what would be expected from planetary transits or other known astronomical phenomena. The mystery of Tabby's star began with observations from the Kepler Space Telescope, which detected the unusual dimming patterns during its mission to identify exoplanets. The star's behavior immediately caught the attention of astronomers because the dimming events showed none of the regular, predictable characteristics associated with planetary transits. Instead, the brightness variations appeared chaotic and asymmetric, with some dimming events lasting days while others persisted for weeks. The spectroscopic analysis of the dimming events has revealed something even more unusual. The star's spectrum remains constant during the dimming periods, indicating that the brightness reduction is not caused by intrinsic stellar variability or changes in the star's surface temperature. This spectral stability means that something external to the star is blocking its light, but the blocking material shows characteristics that are inconsistent with known astronomical objects like planets, asteroids, or comets. Conventional explanations have consistently failed to account for the observed characteristics of these dimming patterns. Dust clouds cannot explain the rapid onset and termination of dimming events, which occur over periods of hours rather than the months or years expected from interstellar material. Cometary debris clouds would create gradual dimming with predictable fading patterns, but the observations show sharp transitions between normal brightness and deep dimming states. The comet explanation faces additional challenges when considering the scale of material required to create the observed dimming effects. Calculations indicate that blocking 22% of a star's light would require a debris cloud containing mass equivalent to hundreds of thousands of comets, all perfectly coordinated to pass in front of the star simultaneously. The probability of such massive debris clouds forming naturally and maintaining the precise timing observed is negligible. Planetary explanations encounter similar mathematical impossibilities. No known planetary system could produce the irregular dimming patterns observed in KIC 846, 2 and 852. The dimming events last too long for planetary transits, occur too frequently for natural orbital mechanics, and show intensity variations that exceed what solid planetary bodies could create. The spectral analysis confirms that whatever is causing the dimming is not solid matter with consistent optical properties. The discovery of additional stars showing similar irregular dimming patterns has transformed this from an isolated mystery into a broader astronomical phenomenon. Analysis of Kepler mission data has identified other stars displaying comparable brightness variations, though none match the extreme characteristics of K 846, 2C552. These stars are distributed across different regions of the galaxy and represent various stellar types, suggesting that the phenomenon is not restricted to specific stellar categories or galactic locations. The scientific community remains deeply divided over the cause of Tabby's star's dimming patterns. Some researchers continue to search for natural explanations, proposing increasingly complex scenarios involving previously unknown astrophysical processes. They argue that the universe contains many phenomena that remain poorly understood, and that extraordinary claims require extraordinary evidence before considering artificial explanations. Other scientists point to the failure of natural models to explain the observations and suggest that the dimming patterns may indicate artificial interference. The mathematical relationships apparent in some of the brightness variations, combined with the coordination observed across multiple stellar systems, create patterns that are difficult to explain through random natural processes. These researchers argue that the evidence warrants serious consideration of artificial explanations, even if such conclusions seem unprecedented. The debate has intensified as additional observations have confirmed the consistency and complexity of the patterns. Advanced photometric techniques have detected microdimming events that occur between the major brightness drops, creating layered patterns that add another dimension to the mystery. These microevents show duration variations ranging from hours to weeks, with intensity changes that appear to correlate with the larger dimming patterns in ways that natural phenomena struggle to explain. Recent observations have revealed that the dimming patterns appear to be changing over time, with some researchers reporting an acceleration in the frequency of dimming events. If confirmed, this temporal evolution would make natural explanations even more challenging, as most astronomical phenomena involving dust clouds or debris would be expected to dissipate or become more regular over time rather than showing increasing activity. The implications of the Tabby star mystery extend far beyond a single stellar system. If the dimming patterns represent artificial interference, it would demonstrate technological capabilities that exceed human civilization by orders of magnitude. Alternatively, If natural explanations eventually emerge, they would reveal previously unknown astrophysical processes that could revolutionize our understanding of stellar evolution and interstellar phenomena. The ongoing investigation of KIC 846-28852 represents one of the most significant challenges in modern astronomy, forcing scientists to confront the limits of current theoretical frameworks while maintaining rigorous scientific standards. The star continues to defy explanation nearly a decade after its unusual behavior was first identified, creating a puzzle that has captured the attention of astronomers worldwide and sparked intense debate about the nature of the phenomena we observe in the cosmos. As scientists continue grappling with unexplained stellar phenomena, other researchers have been analyzing data from much closer to home, where official sources have begun releasing information about aerial encounters that challenge conventional scientific validation. The Pentagon's acknowledgement that unidentified aerial phenomena represent genuine encounters with objects displaying capabilities beyond current human technology has marked a fundamental shift in how these events are studied and understood. For decades, official reports about unusual aerial objects were classified, dismissed, or simply ignored by mainstream scientific institutions. This wall of secrecy has begun to crack as government agencies have started releasing limited data about encounters that were previously unavailable to researchers and the public. The collaboration between government agencies and academic institutions has created a new framework for analyzing unexplained phenomena that combines military precision with scientific rigor. The Pentagon's All-Domain Anomaly Resolution Office works with universities and research institutions to share selected data and coordinate investigation efforts. This partnership has enabled researchers to apply peer-reviewed scientific methodologies to phenomena that were previously studied only within classified military programs. The collaboration has produced joint research papers, shared databases, and coordinated observation protocols that treat UAP encounters as legitimate scientific subjects rather than fringe topics. The sensor data released through official channels has revealed objects with capabilities that surpass known technology by significant margins. Military radar systems have tracked objects accelerating from 0 to over 3,000 miles per hour in less than 2 seconds without producing sonic booms or visible propulsion signatures. Infrared cameras have recorded objects that appear to manipulate their thermal signatures, becoming invisible to heat-seeking sensors while remaining visible to optical instruments. Electromagnetic sensors have detected unusual energy patterns around these objects that suggest unknown propulsion or power generation methods. The technical specifications of these encounters have forced scientists to reconsider what is physically possible within our current understanding of physics and engineering. Objects have been observed making right-angle turns at velocities that would generate gravitational forces exceeding 600 times Earth's gravity, accelerations that would instantly destroy any known materials or biological systems. The absence of visible propulsion systems, exhaust signatures, or heat generation during these maneuvers suggest propulsion methods that operate according to principles not yet understood by human science. Scientific analysis of UAP encounters has identified consistent patterns across multiple incidents that suggest systematic rather than random phenomena. The objects display similar flight characteristics including instantaneous acceleration, silent operation, and the ability to transition seamlessly between aerial and underwater environments. These patterns appear in encounters separated by decades and thousands of miles, suggesting either coordinated activity or common underlying technology. The consistency of these characteristics across different observation methods and geographic locations has strengthened the case for considering these phenomena as genuine rather than misidentified conventional objects. The pattern analysis has revealed behavioral characteristics that appear purposeful rather than random. Objects have been observed responding to military aircraft approaches by accelerating away at precisely calculated distances, suggesting awareness of human presence and capability. The timing of these encounters often coincides with military exercises or testing of new technologies, indicating possible intelligence-gathering activities. These behavioral patterns suggest conscious control rather than autonomous systems or natural phenomena. The ongoing debate about whether these phenomena represent extraterrestrial technology or advanced human projects has intensified as more data becomes available. Some researchers argue that the capabilities demonstrated in UAP encounters are consistent with technologies that might be developed by civilizations thousands of years more advanced than humanity. Others suggest that these objects represent classified military projects involving breakthrough technologies that remain unknown to civilian scientists. The debate has been complicated by the fact that some encounters involve objects that appear to violate known laws of physics, making terrestrial origin explanations difficult to support. The classification levels surrounding advanced military research have created challenges for determining whether UAP represent human or non-human technology. Black budget programs with funding exceeding hundreds of billions of dollars could theoretically develop technologies that appear impossible to civilian researchers. However, the timeline of UAP encounters extends back to the 1940s, predating the technological capabilities that would be required to create such advanced systems. The historical consistency of these encounters across decades suggests that if they represent human technology, the development programs began much earlier than previously thought possible. Government disclosure has legitimized scientific study of previously taboo subjects by providing official acknowledgement that these phenomena exist and merit serious investigation. Universities have established research programs focused on UAP analysis, while scientific journals have begun publishing peer-reviewed papers examining the technical aspects of these encounters. The transformation from fringe topic to legitimate scientific inquiry has attracted researchers from physics, engineering, and aerospace fields who previously avoided the subject due to professional concerns about credibility. Skepticism remains among researchers who question the quality and interpretation of government data related to UAP encounters. Some scientists argue that military sensor systems are optimized for conventional threats and may misinterpret natural phenomena or equipment malfunctions as anomalous objects. Others express concerns about the chain of custody for evidence and the potential for data manipulation or selective disclosure that supports predetermined conclusions. These skeptics emphasize the need for independent verification of government claims through civilian observation networks and academic research programs. The technical limitations of current sensor systems have been identified as potential sources of measurement errors that could create apparent anomalies where none exist. Radar systems can produce false returns under specific atmospheric conditions, while infrared cameras may misinterpret thermal signatures from conventional aircraft or natural phenomena. The complexity of modern sensor fusion systems introduces additional possibilities for processing errors that could create the appearance of objects with impossible capabilities. If some UAP encounters are confirmed as extraterrestrial in origin, the implications would extend far beyond scientific discovery into fundamental questions about humanity's place in the universe. Confirmation would demonstrate that intelligent life exists elsewhere and has developed technologies capable of interstellar travel. The discovery would require complete revision of our understanding of physics, particularly regarding propulsion systems and energy generation methods. The accumulation of evidence from multiple independent sources has created a situation where the scientific community can no longer dismiss these phenomena as isolated incidents or measurement errors. Each piece of evidence, from atmospheric biosignatures to unexplained stellar dimming to official acknowledgement of advanced aerial objects, contributes to a growing body of data that demands serious consideration. Scientific breakthroughs require careful evaluation, and the 5 key discoveries of 2025 each merit individual assessment based on their supporting evidence. The WOW signal has gained new explanations through hydrogen maser flare research, providing natural mechanisms that account for its characteristics without requiring extraterrestrial origins. The detection of dimethyl sulfide in K2-18b's atmosphere represents the strongest atmospheric biosignature evidence to date, though confirmation awaits additional observations to reach definitive significance levels. The ALH-84001 meteorite controversy continues as researchers apply advanced analytical techniques to distinguish between biological and geological origins of its microscopic structures. Europa's subsurface ocean remains unconfirmed pending future missions from NASA's Europa Clipper and ESA's JUICE programs, which will provide direct measurements of ice shell thickness and ocean chemistry. Venus's phosphine detection has faced contradictory results from different observation methods, highlighting the challenges of remote atmospheric analysis. These discoveries collectively demonstrate how the search for extraterrestrial life has evolved from speculation to rigorous scientific investigation, even when definitive answers remain elusive.